Hello everyone. In this video I'd like to pick up where we left off in the last class period. First, I'd like to go over an important fragmentation pattern encountered in electron impact mass spectrometry. It's the retro-Diels-Alder fragmentation. This is the one that I had some difficulty with in class. I indicated that I would figure it out and get back to you. Well, I have figured it out. I want to now illustrate and clarify this important fragmentation pattern. The retro-Diels-Alder fragmentation occurs when the radical cation has a cyclohexene structure. If the radical cation undergoing this process isn't drawn properly, it becomes a chore to figure out the fragmentation pattern. Let me illustrate. It occurs, as I say, in a cyclohexene type of structure. Now, the drawing we have here, though correct, it's not convenient to use when you're trying to figure out the fragmentation pattern. We have to remember that when you have a alkene, the electron that's removed by electron impact is one of the double bond electrons. So let's make an alternate drawing of that. I've been using as a kind of informal convention to draw such a species by having a loop and then a dot in the loop that indicates one pi electron. When you have a pi bond, that's two electrons that lie in overlapping p orbitals. When a stream of electron knocks out one electron, you're left with one electron that lies in the overlapping region of two parallel p orbitals. You could say it's a one electron pi bond, and basically that's what we have here. All right. In showing the fragmentation pattern, it's convenient to use one of the resonance structures corresponding to this. So let me do that now. The odd electron here can be placed on either this carbon or that carbon. Let me start it on this carbon. If the other carbon here is positive. And basically in this fragmentation, it's a bunch of homolytic bond cleavages that occur. So let's start with the odd electron. We're going to shift it to the adjacent bond. Remember, when one electron moves, that's a half-headed arrow. This bond here is going to homolytically break, so one electron from that is going to come over like that and meet this first odd electron, forming a pi bond there. The remaining odd electron comes over and resides on that bond. Then over on this bond, that's going to also break homolytically, so that one electron pops over like that. And now the remaining electron here is going to come over into this bond region here. I can put it in the middle, or for convenience, let me just draw it like that. Behold, this should give us the correct fragmentation products. Just follow the arrows, as they say. And if we follow the arrows, that will give us this. Over here, we basically have ethene, a neutral molecule, and then the other fragment is a radical cation, which I now want to draw basically like this. Well, let me redraw that. My drawing pen didn't work very well. Let's try that again. And that's basically what I want to show. So the starting radical cation fragments in this retro Diels Alder reaction, or fragmentation perhaps I should say, to give a neutral even number electron molecule and a smaller radical cation. And here is the radical cation shown here. There is resonance structures that you could draw to show the delocalization of the pi electrons and the positive charge. All right. Now, what I'd like to do is to move to looking at the various classes of compounds and the general behavior that we see when they're subject to electron impact mass spectrometry. That is, to look at the mass spectra for these classes of compounds and to comment on some of the general kinds of peaks that we see. Next, I'd like to look at alkanes and examine the type of electron impact mass spectra they generate. Alkanes yield an EI mass spectrum with a relatively large molecular ion peak, along with a number of regular fragment signals. They differ by a CH2 unit. Upon ionization, one of the carbon-carbon sigma bond electrons of the starting alkane is expelled to form a radical cation. The electron expulsion produces a single electron sigma bond between one of the pairs of adjacent carbons. In the starting molecule, one of the CC bonds gets ionized. Because the process is random, any of the CC bonds in the molecule can be ionized. There are no restrictions. In the resultant radical cation, fragmentation will then occur at the ionized carbon-carbon bond site in the radical cation. What's the nature of this fragmentation? Well, let me illustrate. I'll illustrate that with a molecule of hexane, unbranched alkane. Not very well drawn. My drawing tools, I'm having trouble with them. That's supposed to be a bond line drawing of hexane. Now, when the stream of hexane molecules enters the instrument, it's zapped by a stream of high-energy electrons, which will knock out one electron from each of the alkane molecules. That electron is going to come from one of the CC bonds. In fact, each of the CC bonds is subject to electron removal. So it's going to produce actually 3 possible radical cations. You can lose an electron from the C1C2 bond to produce this radical cation. You could lose an electron from the C2C3 bond to produce basically that radical cation. You could also lose an electron from the middle CC bond to produce that radical cation. I'm using the convention of drawing a radical cation here as a 1 electron sigma bond, 1 dot in a loop. Alright, what's going to happen is that the radical cation, when it fragments, is going to fragment to a neutral radical and a non-radical cation. And so let's see that for each of these. Here, the most favorable result will to have it break up into a methyl radical and a 5-carbon primary cation. Basically, the one odd electron here is shifting towards the end carbon. Now let's see on the second one. There's two possibilities to consider. One is better than the other ones, but let's look at both of these. The odd electron here can shift towards either carbon. But what I want to do is produce a primary cation and then a longer chain radical. And that will be this. When this odd electron shifts over to the third carbon, to produce a 4-carbon radical. And the primary cation then would be an ethyl cation. Now that's actually the better result. If the odd electron here shifted in the other direction to produce a 2-carbon, an ethyl radical, well, let's look at that, an ethyl radical, and a 4-carbon primary cation, this is not as good a result because the 4-carbon radical is more stable than the 2-carbon radical. The longer the radical chain, then the more stable it is because it can better delocalize that one odd electron. Now this one, I'll let you figure out what the fragmentation products will be. You can do this. All right. Now that's the story with alkanes. Next, going to look at, oh, I misspoke. This is the story with unbranched alkanes. We're next going to look at branched alkanes. And we're going to go ahead and do that next. All right, let's next talk about the EI mass spectroscopy of branched alkanes. Now with branched alkanes, the molecular ion signal will be smaller than what we saw with an unbranched alkane. That's because a branching point is more vulnerable to fragmentation. Fragmentation at a branching point will produce a more stable secondary or tertiary carbocation. Thus, a larger number of branched chain molecular ions will fragment before they reach the detector, reducing the size of the M+ signal. So let's illustrate that with an example. We use 3-methyl-pentane. Now, we're going to see ionization at a branching point. That will yield the most stable cation fragment. And that could occur either with this CC bond or with this. When it occurs with this CC bond, that will actually produce the better fragmentation fragment result. Let's take a look then. So if this CC bond ionizes, that'll produce this radical cation. This radical cation, the most favorable fragmentation would be to produce an ethyl radical and a butyl cation, namely this. This odd electron is going to shift over towards that carbon, away from that, and that will result in a secondary butyl cation and an ethyl radical. All right, now that is the better result than the following alternative, namely this. Suppose that we ionize this CC bond here, this bond. Let's write the result of that. Now, if this is going to fragment, it's going to produce a secondary carbocation, just as we saw over here. But that's going to make a 1-carbon radical, a methyl radical. So here is what would happen with this one. Producing that secondary carbocation. That's not bad. The radical would be a methyl radical. But the products here are not as stable as over here, because the general rule is that when you fragment, you want to produce a radical with a longer chain. A longer chain can better stabilize the odd electron, as it turns out. An ethyl radical is actually more stable than a methyl radical. All right, the next class of compounds we're going to take a look at is cycloalkanes. In cycloalkanes, the molecular ion peak is fairly large. There are mainly two modes of fragmentation that occur here. One, they tend to undergo a 2-bond cleavage to form ethene or substituted ethene and a smaller radical cation fragment. And secondly, in the case of a alkyl substituted cycloalkane, they tend to break off that alkyl substituent as a alkyl radical, leaving the positive charge on the ring itself. So let's illustrate that with some examples. Let's use methylcyclopentane. All right. We remove one of its electrons to form a radical cation. Let's assume that this CC bond has one electron removed. What it's going to do is to then, the bond breaks, produce a methyl radical. The positive charge stays on the 5-membered ring. We have a cyclopentyl cation, an even number electron cation. The other thing that can happen here is the 2-bond cleavage. And we illustrated 2-bond cleavage in a previous class. With the 2-bond cleavage, you're going to see that when this bond ionizes, so that's the structure of the radical cation. We're now going to carry out a 2-bond cleavage. So watch the electron. Alright, this is a 1 electron bond. We're going to shift that 1 electron over to the adjacent bond, fully breaking that bond now. This bond here will break homolytically, so 1 electron with shared moves over to meet this other electron and form a regular pi bond. The remaining electron here, interestingly, we're going to come over and form a 1 electron bond between this carbon and that carbon, this carbon and that carbon. Pretty interesting. So that's going to produce basically a neutral alkene, propene, and what amounts to a 3-membered ring radical cation, which structure we could draw like this. That might look funny. That's a 1, 2, 3 carbons, like a 3-membered ring, with one of the electrons being a 1 electron sigma bond. All right, next I want to look at alkenes. Alkenes tend to show a strong molecular ion peak. Upon electron impact, the electron removed from an alkene is one of the pi electrons in the initially formed radical cation. The ionized double bond, it's really a 1 electron pi bond with a positive charge, interestingly tends to migrate across the carbon-carbon chain. As a result, the mass spectrum of an alkene cannot be used to determine the position of the double bond in an alkene. We'll see an example of that later in the video. A common type of fragmentation that will occur with alkenes is alpha-beta cleavage of the allylic type. Allylic alpha-beta cleavage, we call it. We've saw an example of that in a previous class. So let's see. We have this starting alkene. It's zapped with a stream of electrons. One of the pi electrons is removed. We have the radical cation formed here. And this is the pattern for alpha-beta allylic cleavage. Now, to illustrate that, let's rewrite one of the resonance structures for that. All right. Designation of alpha and beta, remember, is that locate first the outer electron. The carbon next to that's called the alpha carbon. The next carbon over is called the beta carbon. Now, in principle, we could go either direction, marking alpha or beta. Here we want to go away from the positive charge. So I'm going to designate this carbon as alpha and this carbon as the beta carbon. All right, we're going to see a homolytic type of cleavage. And here we go. The cleavage is between the alpha-beta bond, homolytically breaking. One electron like that. The other electron over to this bond. This odd electron comes over to meet that electron. And that's going to produce now this neutral radical. And this allylic type of carbocation. Allylic cation. It's very stable. And that's part of the driving force for this particular fragmentation result. The allylic cation is going to show up as a fragment signal in the mass spectrum. All right, the next thing I'd like to discuss is the electron impact mass spectra of alkynes. Alkynes show a prominent molecular ion peak. A common mode of fragmentation of terminal alkynes is the loss of the alkynyl hydrogen as a hydrogen atom to yield a M-1 radical cation peak. Let's illustrate that. Alright, so we're going to start with our alkyne, subject it to a stream of high energy electrons. One of the pi electrons is going to be knocked out to produce a radical cation. I will draw its structure now. And I could have also drawn it with the other convention I use of drawing a loop with one dot in the loop and a positive charge. Here what I want to do is to write the radical cation in this resonance form. Alright, so let me show you the loss of the alkynyl hydrogen here. Basically a homolytic type cleavage where hydrogen atom pops off and you're left with a non-radical alkynyl cation which has a mass of M-1. Alright, now another common fragmentation mode for alkynes, both internal and terminal, is a formation of a resonance stabilized carbocation called an argillic carbocation. The argillic carbocation is analogous to an allylic carbocation. Right, let's illustrate that. So we've got our radical cation that formed the parent radical cation. Basically, I'm going to use the same structure here. Now this is, again, this is the parent cation. And this is subject to alpha-beta cleavage, similar to what we saw with the radical cations formed by alkenes. So start with the carbon bearing electron. The carbon next to that is the alpha carbon. The one next to that is the beta carbon. And we're going to homolytically cleave the alpha beta carbon bond. Like so. This odd electron will come over to meet this electron. Now that's going to form, in this case, a carbon radical and a non-radical cation, the argillic cation. All right. Structure for that, at least this is one resonance structure, is that if you follow the arrows here, you will come up with that. Now, let me write the name of that: argillic cation. This has a resonance form. Let me draw that in, and we're just going to shift the electron pair here. This is not so much a chemical thing happening. It's drawing the resonance structure. And then, of course, you shift pi electrons. Are going to shift this shared pi pair one bond position over, and I'll come up with this other resonance form. And this form kind of has a more familiar look to it. You got to writing it with a clear carbon-carbon triple bond with a positive charge next to it. So this even number electron cation has resonance stability. All right. All right. The last class of compounds I want to discuss are aromatic hydrocarbons. What we find with aromatic hydrocarbons is that they will typically show a large molecular ion peak. And this is the result of the enormous stability of the aromatic ring. It has low compulsion to want to fragment. So the radical cations it form will survive and make it to the detector intact. At least most of them will. Now there is, of course, fragmentation. There are two fragmentation routes that I would like to discuss. Alkyl substituted aromatic compounds tend to yield benzylic type carbocations. The benzylic carbocation, known to be stable, will, however, tend to rearrange to a different stable aromatic ring, a 7-membered ring cation called a tropylium cation. When there's an alkyl side chain on a benzene ring that's 3 carbons or longer, a McLafferty rearrangement fragmentation will tend to occur. All right, let's take a look at this. Let me use toluene as a representative aromatic hydrocarbon. All right, it's toluene vapor molecules are zapped with high energy electrons, electron impact. Each one will have one electron knocked out of it, namely one of the pi electrons of the aromatic ring. To show this with one of the possible resonance structures, we'll draw that structure for the radical cation. Now, this radical cation is subject to a loss of a hydrogen atom from the methyl group. Let's see, homolytic cleavage basically. And results in a benzyl cation. Put the plus charge over here the way I'm showing the electron shift. Right, basically that. Now this is a regular non-radical cation because the radical cation lost an atom, a hydrogen atom, and so it's now an even number electron cation. And it has resonance structures. Let me draw one of those, showing the more familiar looking way that we tend to draw the benzylic, or benzyl rather, carbocation here. Now this is, as I mentioned before, subject to a further rearrangement. And basically it's a 1,2 carbon shift where this carbon CC bond breaks off and reattaches. And this is giving you now a 7-member ring. And that's called a tropylium cation. So the tropylium ion itself can further fragment, breaking off acetylene molecules and leaving a smaller aromatic cation. All right, let's illustrate the McLafferty type rearrangement that can occur. This takes place when you have a alkyl side chain of 3 carbons or more. And so let me write the structure of the radical cation resulting from electron impact for N-butylbenzene. Alright, one resonance form for that will be drawn like this. It's a radical cation. There's the 1, 2, 3, 4 alkyl side chain. Now, in the McLafferty rearrangement, there is the equivalent of a double bond that would actually be over here, and the carbon attached to that, or atom I should say attached to that, because it can be carbon, nitrogen, or oxygen, is the alpha atom, and this is the beta, and then this atom is the gamma. So the hydrogen here, in fact, is referred to as the gamma hydrogen. Now the designation of the atoms as alpha, beta, gamma can be a little confusing, and I think it's kind of ambiguous the way that they tag them, but that's another matter. We can talk about that later. And this is a McLafferty rearrangement. McLafferty rearrangement fragmentation. It's a fragmentation that involves a transfer of a hydrogen from one part of a molecule to another. And it works like this. The CH bond here is going to break homolytically. A hydrogen atom breaks off, and it's going to bond to this carbon. A donation of electron from that carbon occurs here, and you're now making a covalent bond there. The remaining electron of this bond moves over to that bond. This bond here breaks homolytically with the electron moving over there, and you see you're forming a full pi bond right there. And let's draw the result of that. Oh, I should show this one odd electron moving in this direction here. And here we go. The fragmentation products produces a smaller radical cation and an alkene, a neutral even number alkene byproduct. The alkene byproduct's right here. You see forming a pi bond there, so boom, boom. This part right in here produces that. And we draw the radical cation structure. And one way to draw that would be basically like this. Now also to mention that there's a hydrogen over here to start with, so another hydrogen atom breaks off and attaches there, so this atom now has, this carbon atom has two hydrogens. And then you can draw, of course, resonance for this guy right here. It is a radical cation, smaller than the radical cation that we started out with. All right. So this is an example of this McLafferty type rearrangement fragmentation. All right, that concludes the video. Thank you for your attention. Goodbye.